All right, today we're going to pull back the curtain on one of the most powerful yet kind of hidden ideas in all of computer science. We're talking about the networks that literally run our digital lives.
Have you ever wondered, how does your GPS actually find the fastest route, especially when there's traffic everywhere? Or, and this one's a little spooky, how does a social network know exactly who you might know and suggest them as a friend? I mean, we use this digital magic every single day, but what's the secret? How does it all work?
Well, the answer to all of that, and honestly, so much more, is a surprisingly simple concept from computer science called a graph. And don't let the name fool you, it's not about charts and bars. This idea is the hidden backbone of pretty much everything, from Google Maps to your social media feed.
So what is a graph? At its heart, it's just dots and lines. Seriously, the dots are called nodes, or vertices if you want to get fancy, and the lines connecting them are called edges. The easiest way to picture it, think of a map. Every city is a node, and every road between two cities is an edge. See? Super simple.
Okay, but here's where it gets really clever. We can add extra information to make these graphs way smarter. For example, an edge can be a two-way street, right? We call that undirected. Or it could be a one-way street, which we'd call directed. And even cooler, we can give each edge a weight or a cost. Think about it. That weight could be the distance of a road, the time it takes to drive it, or even the price of a flight ticket. And that one little idea, adding a cost, is the secret sauce that lets us solve some seriously complex real-world puzzles.
All right, so we've got our map, our network of nodes and edges. Challenge number 1, how do we actually explore this thing without just going in circles?
I want you to picture you're dropped into a giant, sprawling maze. Your mission is to systematically visit every single path, every single corner, without getting lost and without visiting the same place twice. How would you even start? Well, that's precisely the problem we call graph traversal.
Now, luckily for us, computer scientists have come up with two main game plans for this. There's breadth first search, or BFS, and depth first search, or DFS. They have totally different philosophies, and you use them for different kinds of problems. So let's dive in and see what makes them tick.
Okay, first up is breadth first search. You can think of BFS as the cautious explorer. It starts at one point and first checks out all of its immediate neighbors. Then it moves one level out and checks all of their neighbors. The best analogy? It's like dropping a stone in a pond and watching the ripples spread out, level by level. And because of this, BFS is fantastic for finding the shortest path when every step or every edge has the same cost.
Then you've got depth first search, and a DFS is the total opposite. It's the bold, adventurous explorer. It picks one path and just goes. It dives as deep as it possibly can down that one route. When it finally hits a dead end, it backtracks just enough to try the next unexplored path and dives deep again. This approach is perfect for things like, well, actually solving a maze, or just figuring out if a path between 2 points even exists.
So, exploring is great. We know how to navigate the network. But what if not all paths are created equal? What about finding the best path? This is our second big challenge.
Remember those weighted edges we mentioned earlier? Well, this is their time to shine. Because in the real world, the shortest trip isn't always the one with the fewest roads. You've got to think about distance, speed limits, traffic, the actual cost of traveling on each road.
And for this, we have a truly beautiful solution called Dijkstra's algorithm. It's a classic. It's what we call a greedy algorithm, which sounds bad, but it's actually really smart. All it means is that at every single step, it makes the choice that looks best in that exact moment. It always picks the next closest spot to visit. And here's the mind-blowing part. That simple, greedy strategy is mathematically proven to find the absolute single best path from your start to every other point. No exceptions.
So how in the world does it pull that off? Okay, picture this. You're at your starting point. At first, the algorithm pretends every other place is infinitely far away. Then, it looks at its immediate neighbors and says, okay, the shortest trip I can take right now is to this place. So it goes there. Once it arrives, it looks at its neighbors and says, hey guys, I just found a new route to you through me, and it might be shorter than what you knew before. It just keeps repeating that process, always jumping to the closest unvisited node and updating its neighbors until it's found the cheapest path to everywhere.
And that's really the core magic right there. It builds its perfect map of shortest paths from the starting point outwards, one node at a time, always expanding from the closest edge of its known universe. It's an incredibly smart and efficient system that is quite literally humming away inside your phone's GPS right now.
Okay, so we can explore a network. We can find the best path inside it. But let's flip the script.
What if you had to build the most efficient network in the first place?
Let's try a different challenge. Imagine you're an engineer for an internet provider. You've got a whole neighborhood of houses that need service. The problem? Fiber optic cable costs a fortune. Your mission is to connect every single house to the network, but do it using the absolute least amount of cable possible. How do you design that layout?
For this puzzle, we have another genius greedy approach, Kruskal's algorithm. And the logic behind it sounds almost too easy to be true. All you do is make a list of every possible connection you could possibly make between any two houses. Then you sort that list from the cheapest connection to the most expensive. And you just start adding the cheapest cables to your network one by one. But there's a catch, a very important rule you can't break.
You are not allowed to create a closed loop, what we call a cycle. Think about it. If two houses are already part of the same connected network, even through a long chain of other houses, adding another cable directly between them is just a waste of money. It doesn't connect anyone new. So the big question is, as you're adding these cheap cables, how do you quickly and efficiently check if you're about to create one of these wasteful loops?
And this is where a super clever tool comes in. It's a special data structure called a disjoint set union, or DSU. Here's how it works. Imagine every house starts out in its own little group, its own set. Every time you connect two houses with a cable, the DSU basically merges their two groups into one bigger group. And its superpower is that it can check almost instantly if two houses are already in the same group, no matter how far apart they are in the network.
So when you pair this DSU tool with Kruskal's algorithm, the whole thing becomes this beautiful, simple process. You grab the next cheapest cable on your list, you ask the DSU, hey, are the two houses on the ends of this cable already connected? If the DSU says no, you add the cable and tell the DSU to merge their groups. If it says yes, you just throw that cable away and move to the next one. You just repeat this until every single house is part of one big, happy, connected group.
All right, let's zoom out for a second. We've gone through a lot here. What's the big takeaway? What is the real power of thinking about the world in terms of graphs?
Well, think about it. We just tackled three completely different but really practical problems. We figured out how to explore massive networks without getting lost using BFS and DFS. We learned how to find the absolute fastest route with Dijkstra's, and we saw how to build the most efficient network from scratch using Kruskals.
And that is the key point. A graph isn't just some abstract thing for computer scientists. It's a lens. It's a new way of looking at the world. When you can model a complex problem, whether it's shipping logistics, your friend group, or even designing a computer chip as a network of nodes and edges, you suddenly unlock this powerful toolbox of ready-made strategies to solve it efficiently.
And honestly, we've barely even scratched the surface today. From mapping the human genome to analyzing financial markets, graphs are the hidden language that describes how everything is connected. So I'll leave you with a final thought. What other hidden networks are all around you in your daily life, just waiting to be understood through the power of graphs? Thanks so much for tuning in.